Well, that leaves us with roots, and we really only look at the square root. So, square root of function x. Well, for a start, we can only find the square root of a positive number. So the first thing will happen in our original graph, wherever it was negative, that's going to just disappear. It's like it doesn't exist when I'm drawing my new one. So with our random graph here, if I want to draw a square root, that bit's going to disappear, and that bit's going to disappear. So really, I'm just finding the square root of that bit, the bits that are positive. Now, the answer will always be positive as well, because I'm finding the positive square root. So I know the answers will always be positive. And this time, the reverse will happen. Because if I find the square root of a number bigger than 1, then it's going to go smaller. So it'll be below the original graph. But if I find the square root of a number less than 1, it goes bigger. So it'll go above the original graph. So it's the reverse of what happens with the powers. It again means 1's a very important number to find where it is on the graph. So square root of 1 is 1, so I can plot those in. My horizontal asymptote in this case, it will get bigger because we're talking about a number smaller than 1. So it shifts up a bit. Vertical asymptote, again, that'll stay there. Now let's have a look at our derivative. Actually, I've got my derivative wrong there, but it doesn't matter. Because it should be 2 root function x on the bottom. But that's all right, the 2's irrelevant in this one. The original graph, f dash x would equal 0, so in my new graph, my derivative is still going to be 0. Because the top of the fraction would become 0. So again, stationary points will still be stationary points at those x values, or the y values will change. But this time what happens at x-intercepts? Well, we're going to get 0 on the bottom of the fraction. So we're going to end up with critical points. It's most likely going to be a vertical tangent. But basically we're saying that the derivative is undefined. It's undefined. Now, let's just have a look at some graphs here, because it can be a bit tricky to go, well, what's the shape going to do? So if you've got y equals x to the power of, and I've just written the power as a over b. So let's have a look at the thirds. So any time where a over b is less than 1. So x to the power of a third, you probably recognise that one, I hope you do anyway, cubic on its side. 2/3 would end up being that sort of cusp shape, because it's got to end up being a positive number. So if a over b is less than 1, what always happens in the first quadrant, the curve will be concave down. Okay? And so you'll end up with a vertical tangent. Well, 3 over 3 obviously is just 1, so you get the straight line. But if that power now goes above 1, the concavity changes. So when you have x to the power of a number bigger than 1, in the first quadrant, you end up with a concave up graph. So you don't actually have a vertical tangent at that point. Okay? You have a horizontal tangent. All right. Why is that important? Well, because if you're now going to find the square root of a graph, if you know what the original graph is, it helps. So if the original graph was x to the power of 4, well, if I find the square root of that, I'm going to get x squared. So actually, even though my theory before said, the derivative will be undefined, well, for this one, no, it wouldn't, because it'll be x squared. Because you find the square root of x to the power of 4, you get x squared. So if you know the function, it makes life a bit easier. Otherwise, you're sort of just guessing what's going to happen. X cubed, well, if I find the square root, I'll get 3 on 2. Well, 3 on 2 is bigger than 1. So it must be concave up. And so I end up with something like this. Now, yes, the derivative is undefined, because it just sort of stops at that point. It's not a continuous. Remember, one of our rules for being differentiable was that the curve is continuous. But this one won't be continuous because you can't find the square root of the negative number. So it disappears in that part. X squared, Well, find the square root of x squared, you get y equals x. You get what looks like an absolute value curve, so you get a sharp point. So again, the derivative is undefined at that point. If I had 5 on 3, we'll find the square root of 5 on 3, and we get 5 on 6, which is less than 1. So now we get a concave down shape. And there's our vertical tangent. And the last one I've got there is 4 on 3, which is 2/3. So it's concave down, but it still exists. We get what we call a cusp at that point. So it comes down in a cusp shape. So it's still got a sharp point. It's not a sharp point like absolute value, but it's still a sharp point it's coming down to as a cusp. So all right, what happens with our random curve then? So my stationary point, well, it's bigger than 1, so therefore the y value will come underneath the curve, so it comes down lower. Now here, I have no idea what these roots are doing, because it's a random curve. It's all subjective. But I guess if I think back to what the original curve originally was, hence original curve, I said original a lot of times then, didn't I? But if you think back, at that root, it was cutting it like a linear function. So logic says, if I was to find the square root of a linear function, I'd get x to the power of a half, which is less than 1. So I should get something that's concave down. And if you look at how you got to draw the curve, yeah, it kind of makes sense that's going to be concave down. So I should have a vertical tangent. Same on the right-hand side of that U shape. Now this one here, again, I got no idea what that original shape is. So I'm going to say, well, it's cutting it like a straight line. I'm going to assume that that's a vertical tangent at that point. Yeah, again, a little bit dodgy trying to get through the points. I might have slightly exaggerated my vertical tangent over here. The whole curve's become a little bit vertical. But that's the sort of thing I was trying to do there. Now, if it is a random curve, then, and you're feeling uncomfortable about whether you've made it concave up or concave down, then write an explanation as to what your logic was behind it, because all they're really interested in is that you know what square rooting the graph's going to do. So if you say, well, look, this looks like it's cutting like a linear function, that would give me x to the power of a half. Half is less than 1, so I know it'll be a concave down curve. Or it looks like my original graph was a parabola, so a double root. Well, I know if I square root a double root, I'll get a single root, so it's going to come in like an absolute value. I think the original curve looked like a cubic, so therefore I did this. But if you explain yourself, then whoever's marking it's got to give you credit for that, because you're showing, yeah, look, you do understand what's happening. It's just that you didn't know the equation of the original curve. So you had to make some guesses here to come up with an answer. Oh, it looks even better now, doesn't it? Hey. Okay. Now the other thing they like to ask, instead of saying y equals the square root of function x, they sometimes say, no, how about you draw y squared equals function x? Which, if you think about it, is the same curve, except now you could have plus or minus the square root, so you get a nice reflection in the x-axis. So that would be y squared equals function x. So if you've got to draw that, you do the square root graph first, and then just reflect it. Okay.